Let's look at a couple of problems associated with motion in 2 dimensions. Problem 1. A stone tied to a string, so that is this stone right there, is made to move in a horizontal uniform circular motion with a radius 1.5 meters. So the radius of this circle is 1.5 meters. And this horizontal circle is at a distance of 2 meters, given there. And this is the ground. If the string suddenly breaks, now remember, this stone is connected to a string that makes it to move like that in a uniform circular motion. And at this position, that string breaks. And the stone flies off and strikes the ground beneath. And in doing so, it travels 10 meters horizontally. So that is from here all the way there until it hits the ground. Now we want to determine the magnitude of the stone's centripetal acceleration during the circular motion prior to the string breaking. So while the stone is still moving in this circular motion, what is its centripetal acceleration? Because at some point the string breaks and causes the stone to move tangentially like that and then fall under the influence of gravity to this ground. Of course, the magnitude of the centripetal acceleration is given by that constant speed u squared over the radius of that circular trajectory. In this case, we know to be 1.5 meters. So from the center of the circle all the way to the trajectory, so that distance is 1.5 meters as given here. So before we figure out what centripetal acceleration is, we need to know what this u is. And that value of u can be determined from the equation of kinematics. So remember, this is a sort of a projectile motion that starts here, ends there under the influence of gravity. We can take the y-axis to be like that and x-axis to coincide with the ground, like that. Now let's write down the x equation of kinematics for this stone. The coordinate changes according to the following equation, because there is no acceleration along the x direction. The acceleration is only due to gravity, and that is downward. Now let's look at the y components for velocity and the coordinate change. Let's start with velocity, or the speed. The speed changes in a following manner. uy. So uy is the component, the y component of its initial velocity. In this case, initially, its velocity is purely horizontal, so there is no uy. Now there is acceleration, is minus g. Acceleration along the y direction is minus g times time. Now the coordinate. The y coordinate changes in a following manner. So a is minus g, so it's minus gt squared. There is no uy, so there is no ut term. And at t equals to 0, the object is here. So the initial y position is quite simply 2. Now we are ready to answer the question. Remember, we need to figure out this u, or that u right there. First, we figure out the time it takes for the stone to travel upon the string breaking. It will start to move in a following trajectory, and the time it takes to go from there all the way as it hits the ground. So that is time of flight. Let's consider capital T for time of flight. As it moves all the way from the top position and as it hits the ground, the y coordinate there is 0. So let's substitute this information in the second equation for the y component. You get 0 equals minus half g capital T squared plus 2. And you see you can figure out the time of flight. The time of flight would be 4 over g square root, or 2 over square root g seconds. This capital T is also the time the stone takes to travel a horizontal distance of 10 meters. So substituting that information in this x equation, we get 10 equals u capital T, and capital T is 2 over square root g. Now from which you can figure out that initial speed. Initial speed is 10 times square root g over 2, or 5 square root g meter per second. Having found u, we can use this equation, the centripetal acceleration equation, to get the magnitude of the centripetal acceleration. Note that magnitude of the centripetal acceleration is u squared, which in this case is 5 square root g, square that, divide by the radius of that circular motion, the original circular motion that is 1.5 meters. And that's going to give you 164 meter per second squared. Now keep in mind we have taken g to be 9.81 meter per second squared. And that solves the problem. Problem 2. A particle's acceleration on xy plane. So this is a motion on xy plane, and the particle's acceleration as a function of time is given by this expression, 3t I hat plus 4t j hat meter per second squared. T is measured in seconds. At t equals to 0, the particle's position vector is given by that expression, and its velocity is given by that expression. At t equals to 3 seconds, find the particle's position vector, so where the particle is, and also the angle between its direction of travel and the positive direction of the y-axis. So we are given the acceleration vector completely. So it's 3t I hat plus a 4t j hat in the unit of meter per second squared. So let's first proceed to determine the general expression for the velocity vector. It is given as an integral of the acceleration vector with respect to time. So substituting the expression for A, you have 3t I hat plus 4t j hat dt. Now we have to integrate this, and that is quite simply 3 over 2 t squared, so that is I hat, plus 2t squared j hat. Do not forget a constant vector. Let's call that constant vector vector c. Now we can figure out what this c is. We are told that at t equals to 0, the velocity vector is that. So v when t is 0 should be your c vector, which in this case is 5i hat plus 2 j hat meter per second. So now we have a complete expression for the velocity vector for any time t. Let's write that down here. So grouping the I hat components as 3 over 2 t squared, or the x component, that is, plus a 5, so that's I hat. So that is this component plus that component, which is part of that constant vector c. Now the y component, or the j hat component, is 2t squared. That's this one, plus 2. So that's the j hat. Next, let's proceed to determine the position vector as a function of time. Now that is just an integral of velocity vector with respect to time. So we know velocity vector's expression. So let's substitute all those in. So 3 over 2 t squared plus 5 I hat plus 2t squared plus 2 j hat, and we need to integrate that with respect to time. Integrating the first term, you will have half t cubed. The second term is just 5t t. Note that this is the x component. Now for the y component, it's 2/3 t cubed, that's this term, plus 2t and j hat, plus a constant vector. Let's call the vector d. The constant vector d is just the position vector at t equals to 0. Because when you substitute t equals to 0, that term goes away, that term goes away, that term goes away, that term goes away, giving you only d. And we know what that constant vector is. The value of r at t equals to 0 seconds is just that, 20I hat plus 40j hat. So that is 20I hat plus 40j hat. Let's substitute that into this equation to get the full expression for the position vector at any time t. Let's write it over here. Grouping the x components, it's half t cubed plus 5t. There is 20 from that d vector, so let's not forget that 20. I hat. Now the j hat is the rest, so that's going to be 2/3 t cubed plus 2t, that's this one, plus 40 j hat. And the unit for the position vector is just meters. Now we can answer part A, the value of the position vector at t equals to 3 seconds. So substitute t equals to 3 in here and you'll get the answer. That's going to be half 3 cubed, so that is 27. 5 times 3, that is 15 plus 20 I hat plus 2/3 t cubed is again 27 plus 2 times 3, that is 6 plus 40 j hat, and that's going to be 48.5 I hat plus 64 j hat measured in meters. Part B, the angle between the direction of travel and positive direction of the y-axis. Direction of travel is given by the velocity vector. So let's determine the velocity vector at t equals to 3 seconds. So substituting t equals to 3 in this expression, we get 3/2 t squared, that's 3 squared, 9, plus 5I hat. And the j component is 2 times t squared, so 2 times 9 plus 2 j hat, which will give you 18.5 I hat plus 20 j hat in the unit of meter per second. Next, to determine the angle, we can use the dot product. When you take the dot product of velocity vector at t equals to 3 seconds with j hat. Now why j hat? J hat represents the positive direction of the y-axis. And that's simply going to be 20. Because when this vector dotted into j hat, this will not contribute because it's I hat dotted into j hat is 0. J hat dotted into j hat is 1, so we'll give you 20. However, from the definition of dot product, we also know that the left-hand side is the magnitude of the velocity vector at 3 seconds. The magnitude of j hat is 1 times the cosine of the angle between them, which is what we want to find, and that equals to 20. That's that 20 right there. The magnitude of the velocity vector at 3 seconds is given by square root sum of the square of the components, 18.5 squared plus 20 squared. And that is, substituting this inside of that equation, we can determine cosine alpha to be 0.734, and therefore alpha is 42.8 degrees. And that's the answer for part B. That solves the problem.